All right. Okay, finally I got everything up and running. All right. Are there any questions about the homework assignment? What homework assignment? It's one try only. So that's why I said, do not turn it in, do not hit the submit button until you're absolutely sure. Did you did you turn in? Okay. Well, talk to me after class. Huh? Okay. Well, the idea is not to give you guys a low score, but to have you guys to kind of really think about it before turning in, and ask questions in class. In case you have any questions. So just talk to me after class. We'll see what we can do. And I'm gonna turn on the other mic. It's supposed to be on. Okay, it is on. It always sounds kind of odd because it comes from only one side, and somebody cranked up the gain a little bit too much. There we go. Okay, I think it sounds a little bit better now. Okay, so are there any questions about the homework assignment other than that it only has one chance to turn in? No questions? Yep.
After it's due, are you going to open it so we can see what?
Yes, I can certainly do that. Yep. Okay. Any concept questions that you might want to clear up just for the homework assignment? Yes, go ahead.
B minus A?
B minus A.
Yeah.
What about it?
I guessed that it will be whatever is left after. You subtract A minus B. But can you walk us through it?
Hmm?
Can you walk us through it? How do you derive the B minus A? I think it was what's left from A minus B, I think.
Okay, so first of all, you start with the definition, right? So-called subtraction or difference between two sets. Okay, so it is directional, so it depends on which one is on the left-hand side and which one is on the right-hand side of the minus symbol. When you have B minus A, then the result is a set of everything that is in B but not in A. Is that okay?
Yeah, but after I went A minus B, which is everything that's
In A but not in B.
B, can you say what's left will be B minus A?
You kind of have to work out a few examples. So I suggest that you come up with a few examples of set A and set B and see if your observation works out for all of those examples. Okay, so that's not a definitive proof, but that's how you start thinking about it, is to give yourself concrete examples and see if a particular truth that I was suggesting is true or not in general. Okay? Okay, so so along with that line of reasoning, so what kind of set A or set B should you think about? Okay, in terms of proving your idea right or wrong. So you can start with something like A is just lowercase ab, and then B is lowercase cd. So in this case, they do not share a single thing. Okay, and see if what you thought is true in this case. Okay, then you have other examples, like in this case, A is ABCD, and then B is a subset of A, and it only has CD in it. see if your observation is true. Yes?
So I think what you mean is when you do the subtraction, the only thing it subtract will be the common element.
Yes.
Okay.
So you, as I said, B minus A is a set. Okay, the result is a set that consists of all the elements that are in B but not in A. So
there may be some stuff in B that's not part of the new set.
there are some stuff in B that is what again?
Let's say you do A minus B.
Yes,
That means everything that's in A that's not in B.
that is everything in A but not in B. Correct.
That's it.
Yep. But in order to really understand the concept, and to think, whether what you theorize is true or not, you have to think of concrete examples, and then go through those concrete examples and see if what you think is universally true works for all of your concrete examples. Okay? Because just to come up with the concrete examples is a way to study for this class. So are we okay so far with that? Okay, cool. Any other questions? No other questions? All right. So I am assuming all of you have kind of read the notes, at least up to what we went through last week, and hopefully, a little bit ahead of the class so that you have read a little bit about what we are going to talk about in today's class, okay? Because I think that will really help you understand the material, during class, and also you just gain a more in-depth understanding of the concepts. So this is the module that we are on at this point. And I had to move my server because I host my AWS server. Embarrassingly, because I decided to upgrade the Debian distribution from stable to unstable, and then AWS does not like it. AWS says, you need to stay with the versions that we support. And so anyway, now it is hosted on the Power server. So if you go to a particular link, it's not working, you just have to change the first part of the URL. So if you just use this part of the URL instead of the arccis.net URL, everything is still there. It's just on a different host at this point. Okay? All right, but I don't think any one of you is reading that far ahead because I haven't changed all the URLs. I have changed everything up to this one and a few after this one, but nobody has complained yet, so that's a good thing. We talked about tuples last time already, so unless people have any questions, I'm just going to move on from where I left off last time, which is what makes a function a function. Okay, that's what we'll be talking about today. All right, so what is a function? Well, one way to look at a function is we know a function is a subset. Now, this is not a proper subset. It is just a subset because there's a bar underneath the proper subset of symbol. So we just know it is a subset of. What is it a subset of? The Cartesian product between the domain and the codomain. Now, how do we know that X is a domain and Y is a codomain? Because I said so earlier in the previous paragraph. Okay, so that's that's one thing that we know. Okay, every single function, at least from the context of this class, is a subset of the Cartesian product between the domain and the codomain. Is that okay so far? All right. Okay. So in addition to this, what else can we say about a function? Okay, so let me just highlight the sentence and then we'll talk about it a little bit here. This is a requirement in order for a function to be a function. Every element of the domain must be mapped to one and only one element in the codomain. Now note that I said one and only one. I did not say unique. Okay, that's important, okay, because whether something is unique or not is not implied in this case. So if I did not say specifically they have to map to unique elements, that means they can all map to one single element in the codomain. It still counts, okay? It's still okay. Yes?
Could you send out the stream link, please?
I did send, I thought I did. Did I forget to click save? Okay. Or I can display the URL now and you can copy it by hand. Are you good? You got it?
Yeah, I got
Okay, cool. All right, so let me give you a few examples what I mean by this requirement. Okay, so I'm going to use this, I can type everything here by using text. So let's say the domain is 1, 2, 0, 1, 2, and 3. Okay, and then the codomain is Y, which is A, B, and C. All right, so we know that the function, any function that has X as a domain and Y as a codomain will be a subset as follows. Okay, so if I say f x goes to y, okay, this is just a notation saying that f is in fact a function, x is the domain, and y is a codomain. Okay, that is just a notation that we introduced in the previous class on last Wednesday. Okay. Now, if I know that f is a function, x is a domain, y is a codomain, now I also know that f is a subset of x Cartesian product with y. So now the question is, what exactly is x Cartesian product with y? Now in this case, it's going to be quite tedious because I'm going to have 12 elements in that Cartesian product. Because I'm going to have 0a, okay, 0b, 0c, 0d, right? Huh? Oh, there's no d. Oh, okay. So one ABC, and then we'll have 1A, 1B, 1C, and so on. So I'm just going to be a little bit lazy and paste it a few times. I think that's more than enough. So we'll go ahead and fix up some syntax here. We got 2, 3, 2, 3, 2, 3, and curly brace. So I did have way too much stuff in here. And then remove the next 2 lines. There we go. Okay, so now we have the Cartesian product, all spelled out. Yes, go ahead.
Above the line where you say f is a subset of x Cartesian product y,
Yeah.
x arrow y, what is
Because f is a function, and I identified x as the domain and y as a codomain. Because of this, f is a subset of the Cartesian product.
I thought you were using like implication.
No, there's no implication. Implication would be double bar, so it would look like an equal and then a greater than. Yep. Okay, so is everybody okay with the Cartesian product kind of all spelled out like this? Super tedious, but you can do it with a double loop, right? You have one loop to go over every element of x, and then for each element of x, you have another loop to go through every element of y, and then you just pair up, okay? Grab one thing from x, grab the other thing from y, pair them together, make a tuple, add the tuple to the set. That's how you generate the Cartesian product. So is that okay so far? Okay. All right. So assuming this is okay, that means we have there are a lot of subsets. Okay. If I just say a subset of, okay, let's kind of throw that out here. Okay. If I know that I have a set of 3 items, okay, so this is kind of like a sidetrack from this main discussion, but we'll get back to this one. So if I just say that I have set, I don't know, T, okay, T has 3 elements, okay, we'll just say that it has element X, Y, and Z in lowercase, okay. My question is, how many subsets can I generate out of T? In other words, how many sets out there are subsets of T? So let's start with, okay, so this is, it's not working. That's okay, okay? Let's start with an empty set, okay? How many subsets do we have? How many set out there is a subset of T? One is correct, because the empty set is a subset of the empty set, okay? So this one has one subset. Okay, let's start with another one, okay? So I'm trying to get you guys to see the pattern, okay? Because that's one thing that I also want to teach is, how do you generalize, okay? You have to start with things that you already know, very simple, and then you move your way up very gradually. And then you notice the difference between the cases and go like, how do I go from here to here? How do they relate, okay? So if I have T being a set only having one single element, how many subsets does it have? It has two subsets, right? Okay, so why does it have two? The empty set and the set of just element A. So I'm going to even include, which subset or what subset we are talking about here. So this one has the empty set and the set that only has A in it. Is that okay so far? Yes? Are we ready to move on to a set that has two elements? Yes?
There's the perfect subsets or whatever, right? Where it's that's
Proper subset.
So wouldn't every subset then technically be a proper subset if you can count an empty subset as a subset of
An empty set is a subset of every set out there. Yes.
Oh, so even proper subsets have the empty one included technically?
No. If you start with an empty set, then the empty set is not a proper subset of itself. No set is a proper subset of itself. Why?
Well,
B minus A has to be that.
Has to be non-empty.
I see.
Yep. Okay, so let's move on to T having two elements, A, B. So this gets a little bit, okay, let's count how many subsets does it have. It can have empty set, right? Everybody likes empty set because it is a subset of everybody. It has a set of A only, right? Set of B only, and then the set with A, B both. So it has got 4 subsets, okay? So we'll enumerate all 4. So it has 4 subsets, okay? Okay, that's supposed to be a comma. And it has got just B by itself and then A, B both, right? Yep.
Is AB and BA seen as the same one?
Yes, because in the set, there's no ordering between the elements, okay? So now we have our example, ABC. So how many subsets does it have? It has 8, exactly. Why? Why does it have 8? Okay, the quickest way and the easiest way to think about this is it has got these 4, right? Because it has just got one extra element. But what about each one of these, but with C in it? With C included, right? So we have these 4, and then another 4 which is just copy and paste, but the pasted version also has C in each and every one of those. And that makes 8. So if I add another element, then we have 16, we got 32, we got 64, and so on. What do you notice? First of all, those are all powers of 2. Okay, and what is dictating that power? The number of elements in the set, okay, or the cardinality of the set. Okay, so that means if I know how big a set is, then 2 to the power of the cardinality of that set would be the number of subsets out there for that particular set. Are we good so far?
Can you say that again?
Okay. So the number of subsets of a set T is 2 to the power of the cardinality of T. That kind of spelled it in English. Yep. Yep. So this is 2 to the power of 3, which is 8. Yep. So the set that we were originally working with has got 12 elements, right? So there are 2 to the power of 12 or 4096 subsets. Okay? Because it's exponential. Are we good so far? Now, what is the other way to look at this? Okay, this one I think some of you would appreciate, especially if you have taken assembly language programming or understand how numbers are represented internally. Okay, so let's just take a 16-bit number into consideration. Okay, does everybody understand what I mean when I say a 16-bit number? Can be a signed or unsigned integer. I don't really care about whether it's signed or not. It has got 16 bits. What is a bit? At a low-level representation thing. Something that can be on or off, but what exactly make up that word, bit, B-I-T? It's a binary digit. Very good. So the B comes from binary, and then the ITs come from digit. So it's a binary digit, okay? So a 16-bit integer simply says, okay, we got 16 binary digits. Is that okay? How many unique values can we specify using 16 bits? 2 to the power of 16. Why? Because each bit is independent to the other bits, right? The bit 0 can be on or off by itself. Bit 1 can be on or off by itself. Bit 2 can be on and off by itself. Is that making any sense? Now, what does that have anything to do with set representation? Each bit can be interpreted as the presence or the absence of the number corresponding to its position. So bit 0 being a 1 means 0 is there. Bit 0 being a 0 means 0 is not there. It's absent from the set. What about bit 5? Okay, well, bit 5, which we normally know as 2 to the power of 5, which is 32, okay, that individual bit is indicating the absence, which means a 0, or the presence, being a 1, of 5. So now with a 16-bit number, you have the most efficient, well, one of the most efficient way to represent a set that can only contain numbers from 0 to 15. Is that okay? So that's another way to look at this thing, because it corresponds to something else that you already understand. Just different ways of looking at the same thing. Are we good so far? Okay, all right. Okay, so we go back to this, we're now back from our sidetrack. So we say, oh, the Cartesian product xy has 12 elements, and therefore there's a total of 2 to the power of 12, or 4096 subsets. That doesn't tell us much. What else do we know about a function? Okay, if I say f is a function, we know it's a subset, okay, but there are so many of those. Do we have any extra restrictions? And the extra restriction, and the most important extra restriction, was the one that I showed you earlier. Okay, so let's go back to that one, and the highlighted sentence is the most important part. Okay, if you want to call anything a function, each element of the domain must be mapped to one and only one element in the codomain. Okay, what does that mean? Well, let's go through a few examples, and you tell me whether each one is a function or not, knowing that x is the set of 0, 1, 2, 3, and y is the set of a, b, and c. Okay, so making those assumptions about the domain and the codomain, tell me whether this is an actual function or not. So I'm going to say, okay. Is that a function or not? Are we sure? It does not meet the requirement. Okay, so without reading, okay, this is perfect because you cannot read the sentence behind it. What was the requirement again? Let me see. Each element of the domain, what is the requirement again? Has to map to one and only one thing in the codomain, right? Okay, we see that 0 maps to A, cool. 1 maps to B, 2 maps to C, all good. What about 3? 3, okay, first of all, is 3 in the domain? Yes. So that requirement should apply to 3 as well, which means 3 is supposed to map to one and only one thing in the codomain. Is not. This is not a function. Okay. Okay, it fails one of the requirements. So let's check out the other one. Okay, we got 0a, 1a, 2a, and 3a. Because TAC is lazy, I don't want to look at the other elements of the codomain. Is that a function? It is a function, because the requirement says only that each element of the domain, okay, we look at each now, each, all right, cool, we got them all covered, has to map to one and only one element in the codomain, right? Is A an element of the codomain? Yes. Is A an element of the codomain? Yes. Is A an element of the codomain? Yes. And I have to say this one because I just want to be complete. Is A an element of the codomain? Yes. What makes it not a function? There's no reason why it's not a function. It is a function. Yes?
So in the top where like a 0A, 0B, 0C, that would be right?
That would not be okay. So let's take a look at that one, okay? So we have 0A, 0B, and 0C, okay? So this one would miss like a few things, okay? First of all, the sentence reads, every element in the codomain, okay? So we'll just consider one element at a time, just 0 for now, okay? Has to map to one and only one element in the codomain. Well, this one maps to 3 elements in the codomain because 0A means 0 maps to A, 0B means 0 maps to B, and 0C means 0 maps to C. So that one single element in what we thought was the domain is mapping to 3 unique elements in the codomain. It is not one and only one anymore. Yes?
So essentially this is the same as the vertical line test on the Cartesian plane as well as like making sure it's a continuous
Yes.
function on a Cartesian plane, right?
Yes. Now you can see the correspondence between functions in this class and functions in your other classes. Now our functions are not going to be continuous, okay, which your other classes are, but that requirement is still there, except we cannot plot it because we are not dealing with numbers or necessarily values that can appear on a graph.
Well, the idea that each element of the domain has to be mapped would mean it would be continuous, no?
No, because it depends on the set, right? Yeah. So we are dealing with values that are not continuous to begin with. Okay. So this one is not a function for 2 reasons. Because it failed the test of one and only one thing in the codomain. It also failed the test of every element in the domain has to be mapped to something in the codomain. So it failed both tests in this case. Is that okay so far? Okay, cool. So is this example helping you to kind of get an idea of what it means when I said each element of the domain has to map to one and only one element in the codomain? Is that good? All right. So now I have a concern of, but how do I specify that requirement? The subset part is easy. Using mathematical symbol, we just have to use the subset of symbol, and we're done with that one. But what about this requirement? Yes?
What about like empty sets? That's an element, right? So
Okay. So the question is, if x, okay, so what if x, do you want the domain or the codomain to be empty? Is a big difference, okay? So you want the codomain to be empty. All right, so if x is ABC, y is the empty set, then there exists no function with x as domain and y as codomain. The reason why there cannot be any function at all with X, in this case ABC as our domain and Y being an empty set as the codomain, is there's no way to map.
What if it's like one of the empty set is one of the elements of the domain? It's like empty set B or empty set 1, 2.
What if Y has empty set?
Yeah, empty set.
Oh, it only needs one element. It can be anything. Then it's possible. Because in this case, then I can map A to the empty set, B to the empty set, and C to the empty set. So I can at least make one relatively useless function exist. But if I have this, then no function can exist because there's nothing I can map A, B, or C to. Is that okay? All right, so let's look at the next one. What if X itself is empty? Our domain is empty. Y is non-empty with A, B, and C. Then there exists a trivial function f being an empty set itself. It still meets all the requirements as a function, even though there's nothing in it. Because, okay, so the domain has nothing, right? Can I still say that I map everything, each element of the domain maps to one and only one thing in the codomain? Yes, I can actually still say that.
What is it technically mapped to?
It's not mapping anything because you did not give me anything to map from. So it still meets the requirement. This is still a function. It is a trivial function that really doesn't do a single thing. Yep.
Another way to look at it is because since a function has to be a subset of the x cross product y,
Mm-hmm.
if you take the cross product of an empty set, you just get an empty set.
Yes. But it doesn't necessarily make it a function because the other sentence holds true because the Cartesian product between x and y would still be an empty set. But in that case, you cannot have any function to exist because there's nothing for A, B, or C to map to.
But in the other case,
Right?
you can map
It still meets all the requirements because you cannot say that, hey, look at this thing here. It's not mapping to anything. What are you talking about? Right? You cannot look at the other thing, go like, it maps to more than one thing at the same time. Nope. It did not fail those tests. So it automatically passes all the tests. And we will still call this a function. So are we good so far with this? All right. So you can see how much time it takes in order to explain a concept like this, using examples, natural language, describing what it is, and so on and so forth. And guess what? One thing that mathematicians do not like: explaining stuff using words. Okay?
It's like explaining like the infinity concept.
As a concept, right? You can only approach infinity. Infinity is not a number. Yep. So, through all of these reasonings, we arrive to this kind of strange conclusion here, and we say this statement, okay, this entire thing is true if and only if f is a function where x is the domain and y is the codomain. Okay, it doesn't quite list y, but that's the general idea. Okay, so we look at this thing here and go like, okay, what is it really saying? Okay, so how do you get started with reading something like that? Okay, we'll take the easy part first. Okay, we'll say, okay, there's a quantifier out here. Okay, so the quantifier says, if I look at every element of x, the following should be true. Okay, so now it goes back to what if x is an empty set? Well, if uppercase x is an empty set, then we automatically meet all the requirements. Okay, so let's say x is not empty. Okay, if x is not empty, then for each element of x, I'm going to evaluate this part of the expression, and it better be true for every element of x. Is that okay? So you look at the part that is highlighted and go like, well, how can that be true or not? Well, because I am just comparing whether a number, okay, Okay, I'm trying to reset the selection. It won't let me. What is going on here? Okay, I just refreshed the page and hopefully it let me highlight again. Okay, so this part here, if you ignore everything, okay, it's kind of hard to specify that part. Okay, it's better to point. Okay, if you look at just this part here, it's the cardinality of a set. Okay, which is a number. Can I compare a number to 1? Okay, so if I compare a number to 1, it's either true, yes, it is 1, or false, it is not 1, right? So now the tricky part is, okay, but what am I comparing to 1? Okay, so so now we'll focus on just this part here, okay? Just including everything that includes the cardinality sign, but not the equals to, okay? Because we want to know the cardinality of what set are we considering in this case. So what is the set that we are looking at? The set starts with the curly brace and it ends with the closed curly brace. That describes a set, okay? And I'm just counting how many things are in that set. We know everything in this set is a 2-tuple. So I'm just going to say, okay, we already know everything is a 2-tuple. We'll just say the first item in the 2-tuple P, and we'll say the second item of the 2-tuple to be Q. So I'm binding P to the first item in the 2-tuple, and I'm binding Q to the second item of the 2-tuple, and go like, okay, so what are the restrictions in order for something to be in this set, okay, other than it has to be a 2-tuple? Okay, so the first thing is P equals to E, and E is already bound here. So we know what E is. E is an element of X. Okay, EP equals to E, fine. So we are now only focusing on the 2 tuples where the first item is the same as E. So the set will only consist of E something, E something, E something if there are several of those. Okay? And, okay, PQ has to be an element of F. Because remember, F is a set that is a function, and we are trying to figure out whether F is a function or not. We think it's a function. We want to confirm it is a function or not. So when you look at these two combined, it is simply saying within this set, the first item is whatever we choose out of X to begin with, and the second item is PQ as a whole has to be found in F. Is that okay? Yep.
So the first part of P equals E means P is an element or any element?
P is an element of X.
P is an element of X.
P comes from the domain.
Does the same thing as say E is an element of X? Or
Because E is already bound as an element of X.
Okay.
Yep. So there's a shorthand to do this. We can just say EQ, and then not have to describe P, but that's kind of hindsight to make it more optimal. Are we doing okay so far with this? Okay, let's apply this to all the examples that we have gone through so far. Okay, so I think this will be helpful to understand what is that expression doing. Okay, so we will look at this one first. Okay, so we'll look at this one, and we'll say, what if E equals to 0? Okay. So we want to look at the cardinality and the expression in general. So what if E, this E here that I have chosen because of the universal quantifier, what will happen to the rest of the expression? We look at this thing here and we ask, okay, give me all the 2 tuples that starts with a 0 and make it a set, right? And how many elements in this case starts with 0? We only got 1. Right? So now we ask, what is the cardinality of that set? 1. 1 equals 1 is true. So 0 is passing that test. Great. But we need every element in X to pass that test. Is that okay? So 1 is going to pass the test, 2 is going to pass the test, but 3 is not. So let's see what happens when E equals to 3. Okay. What happens when E equals to 3? Okay. So when e equals to 3, we plug that in, okay, and we say, give me all the two tuples in F where the first element is 3. Nope, nope, nope. So this set here is going to be empty. It's not false, it's empty, okay? So now we take the cardinality of an empty set, which is 0. 0 equals 1 is false. If the test fails for one item, the for all as a whole is false. Because for all sets, every element has to pass this test. We found one element, 3, out of x that is not passing this test. Guess what? The whole thing fails. And as a result, this particular f here, the first example, is not a function because one element of the domain is failing that test. Are we good so far? Yep.
When we talk about the cardinality of sets, and we have tuples in sets, does each tuple count as one element?
Yes. One tuple is counted as one single element of F. Okay? Let's look at the last one. Okay, so let's look at this one here, and we ask what happens when e equals to 0. Okay, what happens? The set that is described here basically is just saying, go through F, give me all the elements where the first item of the two tuple is 0 in this case, right? So you go through this F and go like, ha, everything starts with a 0. So the set of all the two tuples of F where the first item starts with 0 is going to have 3 elements. Is that okay? So this part here is going to have 3 elements. What is the cardinality of that set? 3. 3 equals 1 is false. Okay, that failed the test. Now, if you plug in what if e equals to 1, it's going to fail the test too, because in that case, we'll have an empty set. 0 equals 1 is false. So it would basically fail that test for every single element. Is that okay? All right. So we like to, in mathematics, okay, we would like to express stuff using expressions like that, and I do understand that normal people do not like to read that because it takes a little bit of training, a little bit of getting used to, and a little bit of effort to start to look at the symbols and try and understand what they mean. Now, how well do I know this preference or the lack of preference, okay, because people do not like to read symbols. So I'm going to digress a little bit and talk about my dissertation. That was a long time ago, okay. I wrote my dissertation. The original version of my dissertation to get my PhD was about 50 pages. Now, if you ask any professor, okay, at a 4-year university, like UC something, they would say 50 pages for a dissertation, that is awfully short. Because remember, they're all double-spaced using 12-point font and stuff like that, so it's really sparse, okay, there's not a whole lot of content. And the reason why I got away with only 50 pages is because I just use a lot of mathematical symbol. This implies that implies that, that implies that, and therefore, using the 3 dots, here, this is the conclusion. So I would say in the original version, 60 or 70% of the text are equations. Okay, proved, equations, propositions, and so on and so forth. I got 3 professors on my committee. Okay, so they collectively would evaluate my dissertation and other things to see if I'm worthy of my PhD or not. Okay, when they first looked at my dissertation, they go like, well, Tech, you got to move all the math stuff to an appendix. And go like, but that's more than half of the dissertation. Then I only have like 20 pages in the dissertation with a 30-page appendix, right? They go like, yeah. I go like, why? Because we don't want to read your proof. We just want you to tell us what you have found. We don't want to go through your proof. Then I go like, but isn't it important to go through the proof so that you can check my logic and see if my conclusion follows the premise or not? They didn't say a single word, okay? But I thought that was pretty important. So you guys will look at this and go like, well, you guys agree with the professors, okay? Who wants to dig through a whole bunch of stuff that looks like this when you can just go through some English sentences, okay? What is the finding? This is the conclusion, blah, 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 okay? So that's great. So let's roll back the time even further, okay? At the beginning of my process to write my dissertation. My advisor told me about a theorem and say, okay, since this master's thesis came up with this particular theorem and is related to your dissertation, you can just start with that. Okay, seems to make sense, right? You don't want to reinvent the wheel when it's already here. Makes sense. So I basically wrote with that for a few weeks, and then one day I just got this kind of gnawing feeling in your head saying that I don't know, this theorem does not seem right to me. Okay, it was just kind of like a gut feeling. And then I told my advisor about this and he goes like, no, this has got to be right, okay, because it's in the thesis of this person here. So I went to dig it up. And the proof was a sentence that starts with obviously. There was no actual step-by-step proof of the conclusion. So it was just obviously. I go like, that's not a proof. I cannot take this. Okay, so I actually went off another week to try to disprove it. Now, disproving is relatively easy if you can find a single counter example. Okay, you just find a case where the theorem is actually false. Okay, then you have disproved the theorem. And I did. I found a counter example. And then my advisor just goes like, oops. I only got a few weeks started on, so it's okay to restart, to basically not make that assumption. It wasn't a big deal to me. I went back to the AI lab, the artificial intelligence lab, and I told another graduate student about this. And he went ballistic, because he already spent 3 years on his master's thesis based on that theorem. Yeah. What he told me on that day, I cannot repeat in the class for many different reasons. So that is kind of why, I personally prefer, things that are very precise, okay? If I made a mistake here, you can tell me, but what about this? Okay, I think you're forgetting this condition. So, I like to make things as concise, but also as precise as they come. All right? How many people are planning to get a graduate degree at some point? Very good. All right. It's actually kind of, at some point, I think it's going to be almost necessary in this kind of weather. All right. Okay, so section 3.2. Yep, go ahead.
Really quickly, why do you think that it will eventually become necessary?
No, it shouldn't take too long. Because we are running out of stuff that does not require an advanced degree to do. Okay, so roll back time even further. Okay, so the first time we roll back time, it was 94, 95 when I was working on the dissertation. So now we're going to roll back time to the 60s before I was born. Okay, the part of 60s before I was born. So that gives you a clue when I was born. So we'll roll back to the time when before I was born. So there were a lot of employment opportunities, even though there were not a lot of computers. Okay, because remember, back in those days, you don't have PCs, you don't have Apple computers, you don't have Macintoshes, you don't have mobile devices, you don't have Fitbits. Okay, so what are the programming jobs? They're all programming mainframe computers. Okay, what do we use mainframe computers to do? Figure out that social security check. Okay. Figure out the taxes, a lot of stuff, that the government has to do. They have the money to buy mainframe computers. Wells Fargo has the money to buy mainframe computers. Yes.
Like a big calculator, right?
Yep, but they were expensive. Okay, but even so, back in those days, they had a lot of programmers. Why? because programming tools were so primitive that it takes a lot of people to get something done. Okay? You write a program. What do you write a program on? Punch cards, exactly. So punch cards takes a while, right? And then you say, I want to run this program, see if it works. Now these days, yep, exactly. It's actually worse than that. But these days, you look at any type of IDE, integrated development environment, you press that green button, right? And it runs. It logs everything for you. If something doesn't work, it highlights, and you can even specify breakpoints. I want to stop here, check out that variable. I want to look at the backtrace, see how it came from the callers and whatnot. Okay, there are even specialized tools to let you analyze the heap. If you say, I think I got a memory leak, there are tools to help you find memory leaks. Okay, so you guys all got all the tools. They're all GUI based. They're all kind of real time because you can stop the program execution like in real time. Back in those days, you submit a job. You come back the next day to look at your output. And then at the end of that day, you submit another job. And then the day following that, you collect the output. So the cycle of making changes and observing the modified behavior of your program is at least 24 hours. So in order for you guys to truly understand that, okay, try this. Next time when you have to do your homework for 4:30 or some other classes, okay, just say, okay, I'm going to make some changes, but you cannot press that green button until midnight once. And you cannot set breakpoints. You cannot set up watch expressions, nothing. So the next day at about 6 a.m., you get to see the result of that program. Then you spend the next 18 hours making changes and then submit that change again at midnight. See how far you can go with that before you go like, no! Now, that's only one of the obstacles. The second obstacle is, what do you guys usually program in? C++, Java, JavaScript, okay, Python, right? Those poor people back in the 60s, they were programming in assembly language. Yep. So that's a slight complication, right? Especially for those of you who have taken assembly language programming. It's just a slight complication on top of everything else. So you can kind of imagine why they needed a lot of programmers. Yes? But these days, one single person with the right tool can outproduce like an army of those programmers back in the 60s. And tools are improving on a daily basis. Yes? So we can kind of anticipate that, as tools get improved, we don't need as many people doing development anymore. Does that make sense? So why would Google still be hiring people to work for Google or Facebook or Pixar? What do you think you need to do to get a paycheck? Innovate, exactly. Yep.
Do you think that academic requirements would change with that? Don't you think the academic requirements would change, like the criteria would change with that though too?
They will only change when they get enough pressure. Go ahead, Nick.
I was going to say Facebook and Google are actually dropping a lot of their requirements in order to hire like children. Really young people are people who just have experience from their own lives. Yeah, they're doing less heavy on the degrees.
There's nothing wrong with getting a degree. Okay, getting a degree gives you a better understanding of all the other things that you probably will benefit from, when you want to become a productive developer. So IBM is one of the first companies who basically say, we don't need a bachelor's degree from our developers anymore because they are developing that expertise in-house. So they have their own way of teaching people how to program. using their own tools, using their own terminologies and whatnot. So there are companies starting to not require stringent requirements of degrees. But when you, even in IBM, okay, if you want to move up to a researcher position, okay, you're researching the next hardware encryption engine that they put into their mainframe computers, do you think they want you to have a master's degree or a PhD in cryptography, some branch of math, and also computer security? You bet they do. Okay, because that's not one of the things where you can self-train, because you have to go through the process, be mentored by certain professors who are already experts in the area. So if you say that, I just want to be a developer, you may not need to become, you may not need a graduate, a degree. But if you want to work for Pixar, okay, what do Pixar do? They do animation. So if you say, but animation is already dead, right? I mean, look at all the game engines that we can do, and what else, what else is there to do? Every single movie of Pixar has one or more elements that people have not done before. It can be the simulation of fog, fire, just running water, okay? There's something, okay? In every single movie, they focus, there are a few things where, oh, this is new, okay? I haven't seen a movie with that type of animation before. And that's because Pixar wants its employees to innovate. Okay? They're super busy certain parts of the year when movies are on the tight schedule. Okay? They have to produce, and it becomes a sweatshop. But the other half of the year, there's not really a whole lot of work to do. Okay? So at least in the past, employees, or at least certain employees, can propose to their supervisors and go like, okay, I would like to spend my time to research, okay, how flames propagate, okay, how to make flames as realistic as possible in an animation. Now, if they have a movie coming up and it has to do with fire, or has a need for that, you might get approved. And guess what? You'll be doing research for about half a year. And to do research at that level, having a master's degree is a must. Having a PhD is highly desirable. Okay? So I think more and more jobs are shifted to that end. The lower end kind of jobs, the sweatshop kind of job, they're disappearing basically, just because tools are improving. So that's a kind of long answer to the question. Is that satisfactory?
If I have more, I can always come to you and help us out.
Absolutely. Yep. So, but that's just my take on the whole thing. Okay, so some people may disagree and go like, yeah, there's still a lot of need for kind of low level but mundane kind of programming. Cool. Okay, so why is this concept important? So the example I'm using here is, how do you prove that a sorting algorithm is getting the job done correctly? Okay, now since CISP440 is a co-requisite of this class, and I think sorting is introduced even before that, right? So most of you know what sorting is. Okay, I give you an array where things can be out of order. After you run the sorting algorithm on that array, then elements should be in order, right? Should be non-decreasing, non-increasing, increasing, or decreasing order, however you want to order those things. Is that right? Okay. So my question is not even about the algorithm itself. It is about, how do you express that the algorithm is getting its job done correctly? Why is that important? Why is it important to be able to express using mathematical language, which is very concise and very precise, whether the outcome of an algorithm is correct or not? I don't even care about the algorithm itself. I just want to know whether it's correct or not. Yep.
You can have the computer check it for you.
So you can have the computer check it for you. That is the right answer. That is exactly what it is. Okay? So if I can have two inputs to this kind of magical program. The first input is a listing of your program, okay, putting into the funnel. The second input is the mathematical description of what the program is supposed to do, feed it into the funnel, and then the machine, this mysterious program, will give me an output. It's either yes, that code will do what this description says, or not. Okay, that would be like really good. Why do you think that is a valuable thing for computer scientists to achieve? Now remember, that program can be a simple program like a sorting algorithm, but you can also throw the SSL engine into the whole thing and describe what SSL is supposed to do, and it will crank out an answer of, yep, that library is going to do what it is supposed to. Why do you think that is important? Yep.
Assuming it's kind of like a proof, I'm guessing it's saying it'll work in like every case.
It will work in all cases. You don't have to test the code using, test cases anymore. Okay, but why is that important in return?
Oh, it saves time.
It saves time, but but there's something even more important. Yep.
Like it proves it definitively, because if you don't use test cases,
Yep.
there's potentially other cases you hadn't thought of.
Yep.
Make it false.
Okay, so the first rule of testing is you never ask the person who's doing the coding to come up with the test cases. Why not? Because if the coder missed something in the original code, that person is going to miss the test case representing those cases anyway. Is that making any sense? So we don't test our own programs. We want somebody else to look at the specification of the program and generate the necessary test cases. Okay, so that's the first thing I want to talk about. So what is the consequence of programs that are not well tested? So I want you to look at this one. It's called hard bleed. Okay, now I'm not going to read up the entire thing. If you're curious, you can go ahead and read the whole thing. But basically, this is due to a bug. Okay, it's not a bug. It's more of a. The lack of anticipation of how a standard can be abused. Okay, that's probably the best way to describe it. Okay, somebody did not check for certain erroneous conditions, and instead of having the program crashing, it can now be used. Okay, that bug or that defect of this program can now be used to look into the keys, encryption keys in an SSL engine. Okay, so if that magical program that I talked about earlier was reality, this would not happen. Because if you can describe what this thing is supposed to do, like, oh, if somebody is formatting a request that is not compliant to the specification, we just reject it. Okay, if we can just check that one thing, this would not have happened. Okay, so how did this happen? You can read the rest to find out, but the most common problem of something like this happening is because a particular standard has two ways to terminate something, a particular field in a packet or a file or something. Two ways to finish it. Okay, one is you can terminate using a null terminator. Now, you guys already know a string in C is null terminated. We know what to do when you say, oh, this string is null terminated. Where does it end? Keep looking until you find that null character. Pretty easy, right? But most of these standards also have a length delimited specification of saying, oh, by the way, this string cannot exceed 255 characters. So both standards apply to some fields within a communication protocol, a particular packet, a file format, or stuff like that. Is that okay? So a coder may look at that standard and go like, oh, okay, I know how to find a null terminator. I'm just going to assume this string here is correct in terms of being shorter than 255 characters, and I'm just going to look for the null terminator. What is wrong with that assumption? Because that's the first thing hackers will find is to say, let's find something that has two ways of terminating, because I bet you some programmers will forget to check one. Okay? So now, it will pass most of the reasonable tests, because the reasonable test will basically say, we're staying within 255 characters and see if the program worked correctly when the input is correct. It will pass all of those tests, no problem, right? How do hackers think? What is their thinking pattern? If there's a box, specifying what is inside the box is the legitimate use of something, what do you think the first thing hackers do? They look at everything outside of the box. So one thing they will do is to go like, well, you got a length limitation, it's also null terminated. What if I give you a 300 character string that is null terminated? The correct response is the program would say, hey, this thing is not supposed to exceed 255. I'll process up to 255. If I don't find a null terminator within 255 characters, reject, okay? Ignore, drop the packet, ignore the file. Don't do anything with it. No harm done, okay? But this program did not do that. It just say, I'm just going to copy all 300 characters from here to here. Well, the buffer only has 255 characters. What's going to happen to the other characters of that string? It's going to overwrite something, right? I don't think that's exactly what's happening with the hard bleed issue. It's a separate, it's a different kind of thing. But it is the lack of anticipation of how something can be abused. So if you can specify how something is supposed to be used, which naturally basically say everything else is not legitimate, then a lot of problems would not have happened. Is that okay? So automated theorem proving or program verification, there are several names to mean the same thing, is something that was really important in the 80s and the early 90s, and it just kind of died off. The reason why it died off was because there wasn't enough processing power. Because theorem proving takes a lot of juice, a lot of processing power. There just wasn't enough processing power, okay? So people just kind of gave it up and go like, okay, this is not doable. Well, how many years have passed since the late 80s? Well, let's see, the 90s, right? So 30-something years, okay? We got a lot more processing power now than before. So something that was not really doable, including neural networks, they are now doable. So people are kind of returning to automated theorem proving now, not only because it is now possible, that we have enough processing power, but also the risks or the stake is much higher now compared to the late 80s, okay? So in the late 80s, think about this, okay? In the late 80s, what is the worst thing that can happen when somebody hacks into something they're not supposed to hack into? Information. They can get your social security number. They can get your information and stuff like that. But the internet was at its infancy at that time. A lot of computers were not connected to the outside world. So you have to be physically, accessing the console of a mainframe in order to hack it. Okay, so we don't have that protection now. Okay, everything is already hooked up to the internet. Okay, 2, what things are computer automated in the late 80s? Not a whole lot. Okay, not exactly a whole lot. Okay, I think cars were just starting to have computer-based engine control. So they were just changing from carbureted engines to electronic ignition in the early 80s. I know because I had a Buick Skylark, terrible car, because it was one of the first cars that got this transition. Okay? And it's not even computer-based. It's really just electronic ignition. It's not even computer-controlled. It's not like the computer is looking at a lot of things and adjust the timing and fancy stuff like that. Not even that fancy. What about now? What can be automated or the computer can control? Think about Teslas. Okay? Then go like, well, what about Teslas? If someone were to hijack into the control system of a Tesla, what can that person do? I would say, forget about line of sight weapons. That is not a big problem. Why not?
They did a test where they hired somebody to try to hack it, and they ended up taking control of like the windshield wipers, like turning on like the water and all that. They said it was really scary. Like
I think Dodge.
yeah, it might
Yeah.
have been Dodge.
Yeah, it was Dodge that was able. People were actually able to steer the car remotely, but only up to a certain speed, because after a certain speed, the safety kicks in and you cannot be remotely steered anymore. So Tesla is already bad, right? Because it is a car. If it runs into a bunch of people, a lot of people can get hurt, right? What do you think the 18-wheelers are? Which direction do you think 18-wheelers are going? They're all going to be automated. In fact, more priority is put onto 18-wheelers than your Lyft or Uber. Uber's project to automate cars was targeting 18-wheelers. They were not targeting passenger cars, because there's more money in hauling, in transportation. So now you can think about an 18-wheeler carrying who knows how many gallons of gas, diesel, liquefied, compressed, petroleum gas and stuff like that. And if you can get hijacked remotely, okay. So we got a lot more at risk, when security issues, is brought up. Okay, the power grid itself is mostly computer controlled. We have smart power grid now. Now anything that is smart is also automatically susceptible to be hacked. The Navy has autonomous drones where they can complete a mission on its own. Okay, you don't need a room of people, with people behind people, with more people behind those people to direct, the drone operation. You press a button, point and click, and you wait for the drone to come back by itself. So we are already at that stage, and computer security is super important. And being able to prove a program works correctly, regardless of the input, without having to throw test cases at it, is really super important at this point. Yes?
It's kind of like a two-parter. Do you think that automated theorem proving is an issue of computation, or an issue of being able to construct a way to relate the program to a proof and prove it?
Okay, that's a very good question. So the question is it an issue of computational power, or is it because it is an issue with method, okay, the algorithm to prove theorems? So what we'll do in this class is we'll look into propositional logic, okay, and many other classes will probably look into propositional logic too. But the way I focus propositional logic or proving in this class is, can we automate it? Okay, so I'm going to give you a presentation of how to encode statements, okay, Boolean expressions, so that we can actually automate it using a reasonable algorithm. So we'll address a little part of that particular question, is because we still got about 5 minutes, so I can actually finish this part here. So in automated theorem proving, one of the things is, okay, I'll present it this way now, but then we'll look into it further, as we go along in this class. Okay, it's kind of like finding a needle in a haystack. Okay, then you go like, well, most problems are like that, right? Finding a needle in a haystack. But if you do not present the problem correctly, then you don't even know the size of the haystack. So the haystack itself is infinitely large. If I ask you to find a needle in an infinitely large haystack, isn't that a problem? Because the needle may not even exist, but you can keep looking, but there's no limit to how big the haystack is. So you can never terminate and say conclusively and say, Tech, you just tricked me. I know that needle is not here. Or, it's here somewhere. I just need a little bit more time. You cannot differentiate between those two cases. So when we get to propositional logic in this class, we'll have a way to represent the problem so that the haystack itself has a fixed size. Now, is it small? No, I wouldn't say small, but it is finite. But at least with a finite haystack, you can exhaustively search and you can conclusively say, yep, the needle is here, I just found it. Or you can say, nope, I can confirm the needle is not there at all. Okay, so that kind of addresses one of the issues that you mentioned. Go ahead.
Oh, me still?
Yeah.
Okay. I was gonna say, so what you're saying basically is the idea is being able to construct the entry points and stuff of the program that you're building basically, and then knowing which test cases would.
It's not about test cases. It's about looking at the statements in C, C++, whatever programming language you have, and then mathematically deduce what has to be true in the next statement, what has to be true in the next statement, what has to be true in the next statement. So it's basically applying mathematical theorem proving to a program. So you start with a set of preconditions, and you can say that we assume da 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 da. Okay, that's the assumption. And then you derive the theorem along the way. So when the program terminates, you have a terminating condition. So now the question is the terminating condition consistent with what you want the program to do? So you have to be able to specify what you think the program should do mathematically so that you can compare the terminating condition with what you want. So we'll get into a little bit of problem solving, proving in this class, automated proving in this class, when we get to propositional logic, CNF, which is conjunctive normal form, resolution and stuff like that. Those are all in the notes, okay? But since I crashed the server and I haven't have time to update all the links, so if you encounter the problem that I was talking about, the link is not working, just replace the first part of the URL, let me know, and I'll go fix the class link itself, okay? So I'll see you guys on Wednesday, and try to read ahead of me, okay?